So welcome to the final part of today's lecture on the Gram-Schmidt process. And in the last lecture, we just kind of left with this particular setup where we have a vector space W, this red blob, spanned by A1 through A2, and we have a vector U, and we can project U down onto W, and we want to project it so that this vector, the blue vector, is orthogonal to every vector in W. And so the question is, okay, this is what we would, this is an interesting object. Can you find such an object? And it turns out that you can actually find this in a special case. Suppose that W is given by a span of P vectors, and you also know that the span of A1 and AP are orthogonal. Well, you can actually find then what this particular vector is. What does U project down to? So the formula turns out to be given by the following rule. So U times dotted with A1 dotted with A1 times the vector A1 plus U dotted with A2 dotted with A2 with itself times the vector A2. So remember, these are all my coefficients. That shouldn't look, there we go, get rid of that. And keep going. And we have U dotted with AP divided by AP dotted with itself times AP. Now this formula here is starting to look like something we would have seen in the Gram-Schmidt process. Okay, so let me kind of tie things all together here. But the point is, we're not going to prove it, but it can be proved that given any vector U, you can project it down. And then you could actually prove that this is the closest point inside of W to the vector U. And not only that, then the vector that you get by taking U and subtracting this vector, you're getting a vector that's orthogonal to every vector in W. So let's make this clear, the connection to the Gram-Schmidt process. At step P in the Gram-Schmidt process, we are computing the vector VP, which is the vector XP minus, and I'll write it like this, XP dotted with V1 dotted with itself times the vector V1. And I'm going to put, kind of pull the negative sign out, so then I'll have a whole bunch of positive signs here, or additions. So the next coefficient is V2 dotted with itself times V2 all the way out to XP dotted with VP minus 1 over VP minus 1 dotted with VP minus 1, and that's the coefficient of VP minus 1. Okay, now if we step back for a second and stare at this, then notice that this part here is the projection of XP onto the span of V1 through VP minus 1. And now what we want to notice is that as you're adding your new vector, you're making things orthogonal. So V1 through VP is orthogonal, so you're actually using this formula down here. So that is explaining this. And now because you're subtracting, right, you want to think of the U as being the XP here. So because you're subtracting, you're taking this vector, you're taking your XP and you're subtracting the projection, and what you're left over is going to be orthogonal to everything in W. So let me write this over here. So this guy right here is going to be the vector orthogonal to every vector in the span of V1 through VP minus 1. So now what this means is VP is now orthogonal to the things that you have, and so you have a new vector that's still kind of in the span of V1, in the span of X1 through XP, but it's now orthogonal to everything that you've seen before. Okay, so that's the rough idea of why the Gram-Schmidt process works. I know that we're kind of skipping some details here, namely like why these formulas work, but what you want to think of is you're taking your first vector, and then you're taking your second vector, and you're finding out what you're projecting it down onto the first vector so you can find something orthogonal to the first vector. Then you have a space spanned by two things. You project your third vector into that space to find something that's orthogonal to the first two, and you keep repeating this process. And that's roughly why the Gram-Schmidt process works. Okay, so just to kind of reinforce the process, the Gram-Schmidt, I thought I'd just do a very simple example to end today's lecture. Let's say we're giving a basis 1, 0, 3, negative 5 for my space R2, and I want to compute the an orthogonal basis. So V1 is my first vector, so it's just 1, 0. That part's easy. And then V2 I get by taking x2 minus x1 times v1 dotted with x1 dotted with x1 and times v1. And so here I have the vector 3 minus 5. I'm dotting this vector with that vector, so I get 3 upstairs, and then I take the length of the vector downstairs, 1, okay, and then I multiply it by 1, 0, and I get the vector 0 minus 5. Okay, and maybe a little picture will help here about what we're doing. Let's see if I can quickly sketch out what's happening. Make sure everything is roughly in the right order here. So my first vector is 1, 0, right? So there's my first vector. This is the vector 1, 0. My second vector was 3, negative 5. So let's say we use it over here. So 3, negative 5, this is not to scale. Okay, so 3 minus 5. And what you're doing is you're projecting it down here. You would be projecting it onto the red line. So because remember 1, 0 projects a red line. And so what we want is, what is this vector right here? So here, I'll highlight these things here. So this guy here, this would be the projection. Oops, go back. The projection of 3 minus 5 onto 1, 0. And then this is the vector here. This vector orthogonal to the vector 1, 0. And if you stare at this for a second, this vector here is going to be the vector 0 minus 5. So there's a bunch of key ideas from today's lecture. Of course, the first one is the Gram-Schmidt process in order to find an orthogonal basis, and the second one is the notion of projection. So this finishes our slight detour into chapter 6 about good bases, and we'll go back to chapter 4 in the next lecture when we talk about dimensions of a vector space. I will see you in lecture 26.